Hello again, and today we are going to discuss non-binary modulation types. So basically, the modulation types which we are using nowadays for modern communication system, such as Wi-Fi networks, 4G, 5G networks, cable television, satellite communications, and many other applications. That's exactly where we are using these non-binary modulation types. And so we will discuss that today. Our sixth practical exercise will also be about these modulation types, and hopefully that will provide you a lot of information, to at least basic information to understand how these modulation types work and why are they so widely used today. So previously we have discussed binary modulation types such as binary amplitude shift keying, binary frequency shift keying, binary phase shift keying. And now, however, we are going to assume also, let me first remind you that for binary communications, we had only two possible signals, which were different either with amplitude or frequency or phase, depending on the modulation type. And each of these signals carried only one bit, right? So we had signal S1, which represented 0, and we had signal S2, which represented 1. For non-binary modulation types, we now can load much more than just one bit into each signal. And also, we will need accordingly much more signals for this. So the idea is very simple. This allows us to increase the data transfer rate. So basically, we want to transmit data faster. So now, instead of two signals with one bit per each signal, we design 4 different signals. For example, they can have different amplitude. So basically here we, for example, would have 5 volts. Here we would have, let's just say, 2.5. Well, actually, let us make it like uniformly distributed. So here we will put 6 volts. That would be 4 volts, 2 volts, and 0 volts for amplitude of the carrier signal. And that voltage is then multiplied by the carrier signal with some carrier frequency, F0. Right? And this is basically amplitude shift keying with 4 different amplitude levels from 2 to 6, right? And each of these 4 signals with different amplitude now carries 2 signals, 2 binary symbols, 2 bits of information per each, right? So as you can imagine, nothing is stopping us from making 8 different signals, and then we can put 3 bits and send them with the same time duration as before, right? So basically now we can transmit data twice as fast compared to, for example, binary amplitude shift keying, which is good. And actually, that's not where we are going to stop. So the idea is pretty simple and straightforward. We are going to use more signals, and usually we take number of signals, M capital, as a power of 2. Well, because from the information theory, you already know that this way, power of 2 allows us to for these binary symbols represented by some rectangular pulses, this allows them to carry the maximum information amount, which was calculated as an entropy, if you remember, and that entropy also, if you remember, was usually some fractional number. So, for example, let us say 3.21, right? And for that, you needed to use 4 rectangular pulses in order to transmit these 0.21 bits of information. You still used the entire pulse. So we are interested to utilize up to the maximum possible way each rectangular pulse, and for that, for example, if we used 6 different signals we would still have to use 3 bits per each, right? That would be third, that would be fourth signal, fifth signal, and the sixth signal, right? So 6 different signals have these different payloads, right? For each signal, different payload. However, you know that for 3 bits we can actually create even more payloads which are not used, for example, in this case, right? And this is a bad idea. Actually, instead, we should create 8 different signals and utilize up to the maximum possible way these most significant bit, because these 2 last bits, they are utilized to the full extent. This, however, as you can see, wasn't utilized completely, and that is bad. So that's why we usually take this number of signal as a power of 2. And let us start from a simple thing. Hopefully you remember what was the line coding. If not, let me fast remind you that we used pulse shaping for data, such as, for example, non-return to 0 or AMI encoding. We have already talked about that, and this example is non-binary. So if before we are talking about only binary line codes, both NRZ, AMI, Manchester code, they were binary codes, right? So meaning they only had 2 or 3 voltage levels corresponding to 1 or 0. Now for DV, 2 bits per 1 quaternary symbol, it's how it's called, 2B1Q code. Now we have 4 different voltage levels, as you can see here, and each voltage level carries 2 bits. So basically this number Q quaternary means 4, right? So, and B means binary, which is 2. So we basically put 2 bits into 1 quaternary symbol. And that's why it's called 2B1Q code. And the idea is that we can design this coding in 2 different ways. Let us first see this example, which is shown here exactly at this picture. So here you can see that we are transmitting data 0, 1, 1, 0, 0, 1, 1, and 1, right? So these 2 binary symbols, instead of sending them in binary mode, which would occupy 2 time symbol time intervals, right, from 0 to 2 intervals, we now instead compress them into shorter signal with different amplitude levels, right? So you can see here, for example, 0, 1 matches this voltage level. Next signal, 1, 0, matches another amplitude level of 2.5 positive voltage. Next symbol is again 0, 1, which is again this level of minus 0.8 volts. And the last one matches this level. Level 0, 0 was unused in this example. However, it corresponds to this minus 2.5 volts if that would be a case, right? So, and in this example, we are keeping the symbol duration the same. So basically, we had previously, let us assume, for example, this duration was, for example, 1 microsecond. And we are going to keep it the same for this new signal as well. So symbol duration is also 1 microsecond. It's the same. Now, however, information payload here was 1 bit per symbol, and here there are 2 bits per symbol, which basically allows you to send twice as much information in the same time span, right? Also, Also, wait a minute, I think this picture, the symbol is equal to time the binary, right? That's what we are talking about right now. So this is an error of 2. Therefore, spectrum bandwidth is also the same, because as you remember from Nyquist condition, it's actually a reverse of a symbol duration, right? So if symbol duration didn't change, therefore also spectrum bandwidth also didn't change, right? So basically that was an error, right? So Ts is equal to Tb, and therefore spectrum bandwidth is also the same. However, now we are sending 2 information bits per symbol instead of 1. So our data rate is now twice as fast as before, right? That is because actually new binary symbol occupies half of this duration, and basically we now send 2 bits per 1 time unit. That is the first example. Here we are. Here we can see the same information which I just told you, maybe more detailed, right? So signal duration is left the same, not changed, right? Which can be also named just T, for example, right? The bandwidth of first signal and the of coded signal and original signal are the same, because this number is the same, right? And well, therefore this is a constant. We didn't change bandwidth. However, now we send 2 bits per information symbol, and therefore, or in more general case, we send m equal to log 2 of m capital bits of information per symbol, where m is the number of possible signals. Well, in our case, the m is 4, right? So therefore, m small letter is 2. That's the first example. However, we could also do differently. We could have kept the original data rate. So we didn't increase the data rate. So as before, during the time of 2 binary symbols, both in the first and in the second case, we sent 2 bits, right? So basically, the data rate in this case R1 and data rate in this case R2 are equal. So we don't increase the data rate. However, in this case, we would also have something to win, which is, in this particular case, the bandwidth, right? So the second signal would utilize only the half of the bandwidth compared to what was before, which effectively enables us to create a second channel with the same data rate. So we would have now in this delta F binary bandwidth, which can be graphically showed as some bandwidth in the frequency domain, for example here, right? That is this value. And now we have used this code to reduce the bandwidth without affecting data rate, and effectively now we have this new bandwidth of delta F symbol. And therefore we can actually use the remaining part of the bandwidth for the second signal with the same bandwidth. And now, instead of sending 1 signal with data rate R, we send 2 signals with data rate R. So basically, the total capacity of system is still double, right? Only in this example, we divide this capacity between two users, but in the first case here, we gave all the capacity to a single user. So basically, either way, we increase the data rate of the system, of the total system. And in more general case, the bandwidth economy, the bandwidth winning gain would be exactly M, where M is the number of bits per symbol. So either way, this enables us to send data faster. So, as I have told, either we increase the number of channels, each with data rate R, and basically this way the total data rate would be R multiplied by M, or we can increase the data rate of single channel by M times, which basically would be M multiplied by R either way, right? However, this also has some drawbacks. The main drawback is the lower distance between signals. For example, if we compare this to NRZ coding, which was plus 2.5 volts and minus 2.5 volts, and only these two levels were correct levels of the signal, we had this large difference between signals. Now, however, the minimum distance between signals is here, which is much lower, as you can see from these two pictures. Therefore, errors will happen also more often in this case, right? So we only use these methods when we are sure that we are sending, for example, over a short distance, or maybe we have optical fiber with less interference and so on. So we need to be aware of the situation of the noise, because, well, noise immunity is lower, and the more different levels we'll take, the worse situation becomes, right? So here we have to be also very careful. However, for example, let me tell you that in Wi-Fi system we actually have different modes. I think there were like 5 or 6 modes with different modulation types. Amongst them, we had binary phase shift keying as the most robust method, but also the most the slowest method, right? Which works when you are quite far away from the access point, or maybe there is a lot of interference and the signal is weak, and that's when we not particular we as users don't do that, but the Wi-Fi receiver itself sets modulation type to this, right? And then it allows you maybe not too fast, but anyway to send the data and receive it without errors. Here we also have plus coding for error corrections, right? Naturally, some errors happen and some of them can be corrected. Then we have different modulation types, of which we will talk today, such as QPSK, QAM-16, QAM-64, which send more bits per symbol. In particular, QPSK sends 2 bits per symbol. QAM-16 sends 4 bits per symbol, and QAM-64 sends 6 bits per symbol. So basically, QAM-64 is 6 times faster than binary phase shift keying, but also more susceptible to noise. This works when you are quite close to your access point, and well, there is little signal fading, and signal is strong, and everything is okay, and we can afford to use this modulation type, of course, with some coding as well. Even more so, there are different codes for different modulation types. So this coding and these codings are not the same. And well, the receiver and transmitter discuss over the protocol which method should be used in which particular case, right? So basically, these methods can be used if we are not far away. And let us talk more about Quadrature phase shift keying, which is QPSK, of which I told exactly right now when I told about Wi-Fi networks, right? What is QPSK? QPSK is actually the further development of the binary phase shift keying. In binary phase shift keying, we had two different signals, and if we draw them in the complex plane, for example, they were on the same axis, but had different phase, and the phase difference was p. Now QPSK is very similar, except that the phase difference now is p divided by 2. So we divide all the circle of 2p to 4 points, right? And that leaves us with p divided by 2, the angle between 2 points. So that would be QPSK constellation diagram, right? So we will call this picture as constellation diagram. And each of these points now previously had only 1 bit per point, 0 or 1, now can contain 2 bits. Right? That is all the possible combinations of 2 bits per each point. And basically, each signal has different phase shift. So, for example, first signal has no phase shift at all. So basically, we can write as if here was 0, right? Next signal has phase shift of p divided by 2, which is roughly the same as cosine instead of sin, right? Next signal has additional p divided by 2, so basically this p can be represented as p divided by 2 plus p divided by 2. Right, so for each additional signal, for each next signals, we add extra p divided by 2, which represents minus sinus, and basically that is actually binary phase shift keying of these two signals, right? Binary phase shift keyings, as we have discussed it before, right? So we have different phase for these two signals. And similarly, there is another binary phase shift keying between these two signals. So basically, QPSK can be considered to be superposition of two binary phase shift keyings in a very similar way as we have considered binary frequency shift keying to be a superposition of amplitude shift keying 1 and 2 plus BSK 2, right? Sorry. Now, however, each of these signals contain 2 bits per symbol instead of 1, and there is total of 4 such signals. However, we are not practically using this method, right? Although this is very simple and intuitively understandable way to generate these signals, in practice we use a so-called quadrature approach, of which we also have talked a little bit when we discussed mathematics, such as analytical signal, quadrature receiver, and today we are going to use that. So basically, we rotate our points. So let me mark them as we have them beforehand, right? Here, we had them here, here, and here. So we apply additional rotation of p divided by 4, and this way, this point becomes here, this becomes here, this one is here, and this one is here, right? And this approach allows us generation of the signal and optimum receiving at much easier way. So also please note that here we assign these binary payloads to each signal in a very specific way. we make sure that there is no situation that between these adjacent symbols, right, which are near to each other, neighbor symbols, there is always a difference of only 1 bit. So there is no case when we have, well, for example, 0, 1 and 1, 0, like this, right? When we had different here and here in both positions. No, only one position is different for each pair of the neighbors. So between these two, only this symbol is different. Between these two, only this symbol is different. These two have this symbol different, and these two have this symbol different, right? So only one symbol difference per pair. It's okay that these symbols are different in 2 positions because the distance between them is much larger than between those. We need to make sure that we protected the weakest signal, right? So the signals which are easiest to misinterpret, to mix, yes. So obviously here is the lower distance, and more often this signal will become as this signal rather than this signal will become as this signal, because they are quite protected and have actually opposite phase, which is this way. This one is actually as strong as binary phase shift keying, which is the strongest possible modulation type, as you know. So this approach, when we assign these symbols in this specific manner, is called gray mapping or gray coding, and you can actually check this Wikipedia link and see how these codes are designed and how they have been used. So let me show you, for example, that actually it was used mechanically, right? So here you can see some disk with transparent and non-transparent sectors, and basically that is the gray coding. So if we assume that this, for example, is 1, 1, 0, this would be 1, 1, 1, this would be 0, 1, 1, 0, 1, 0, and as you can see, the difference between the neighbors is just in one position, right? Also, quite visually understandable how this code is generated. And there is also given a method how to actually calculate that in the program, right? So if you need these codes, you can design them according to this link. Now, in practical way, we generate these according signal points in quadrature way by adding both sine and cosine signals, right? So each of these points has its own projection to the y-axis and projection to the x-axis, right? And we use them to multiply accordingly. X-axis is multiplied with cosine, y-axis is multiplied with sine. And that's how our signal is generated. Even more so, these projections can actually take values either +1 or -1, which is nothing else than NRZ coding, right? So this gives us this formula that each signal can be calculated depending on the signs of these functions. So if we have, for example, here plus and plus, we would get one of these signals, which can then, according to trigonometrical formulas, convert it into this, right? If we have plus and minus, then we would have next one. Then we can have minus and plus here, and minus and minus, last one, for example, right? I'm not saying that it's exactly this way. You should check and calculate, but either way, it's possible to check which is which, right? And here, plus and minus is just a multiplication with +1 or -1, which are NRZ levels. right? And we have this way these 4 different signals with p divided by 4 initial phase shift, right, which represents this point. Here is p divided by 4. Next one would be 3p divided by 4 here, then here, and lastly here, right? So that's how we generate these signals. And that's because we actually can generate them with the same generator, right? Which generates at some specific frequency omega 0 or 2pf0 in linear scale. And well, actually, additionally, we can represent this signal in a complex form, right? So we actually can even omit this, and that's exactly how we are going to do in our practical exercise today, and work only with these voltage levels. We are no longer forced to simulate the carrier. So if you remember that, then during our last work on the course project, for binary amplitude shift keying, binary phase shift keying, for bare estimation simulation, we created the harmonic signals, carriers, right? We performed the optimal receiving by calculating accordingly the voltage level and comparing it to some threshold, and nothing of that would be necessary if we were able to use the analytical signal form. And for these phase modulation types, it's quite easy to do so. It's not easy to do for frequency shift keying, or maybe for amplitude shift keying, it's not so easy. But it is easy for phase shift keying, for quadrature phase shift keying, and for quadrature amplitude modulation. And today you will see for your own eyes that it calculates the same amount of symbols much faster, right? So that's the idea. And well, we already discussed the analytical signal, and basically these two components, sine and cosine, are actually nothing else than a so-called Hilbert pair, right? If you remember, we discussed that in one of our lectures, that we can use Hilbert transform and make analytical complex signals. So what that means? That means that instead of adding noise to this modulated signal, we can add noise directly to +1 or -1. Just one number can be noised, and then we can compare it with the threshold. Effectively, that would give the same result. If you actually try that for binary phase shift keying with signal to noise ratio calculation by standard deviation, as we have done that in our practical exercise and course project calculations, then you would see that actually that would give the very same bare value. Well, of course, accordingly, you would need to calculate new signal energy, which is 1, right? In our case. So that's working, right? And let's see how this signal is created by hardware means. So the idea is quite simple. We have the data flow of 0, for example, 1, 1, 0, 1, and so on. And each of these even number values gives to the cosine channel. That would be second or fourth, and so on. Each of the odd values go to the sine channel. That would be no, wait a minute. It's reverse, right? Ah, no, it's actually correct. Everything was correct, right? right? So each odd number, we start numbering from 0, which is even number, right? Goes to the syn channel. And in order for these two signals to come at the same time, because as you can see, this 0 came before this 0, we introduce a delay line here, which delays our symbol by one position. So this way, effectively, here we have 0 at the input, here we have nothing yet. When we have 1 is 0 here at the output of this delay, then the 1 comes to here, right? And they arrive to these QAM blocks simultaneously, right? So we need to wait and keep this symbol for the time before we receive the second symbol, because this diagram requires to know two symbols, right? QPSK symbol, also called D-bit. And once we know it, we can modulate it. Now, amplitude impulse modulation in this particular case is nothing else than actually an RZ code. So we convert 0 to +1, 1 to -1, and that's how QAM is performed for QPSK. Then we multiply with the signal generated by the generator. Generator generates syn signal. However, here you can see a so-called phase shifter, which changes the phase of the signal by p divided by 2, thus converting it into cosine signal, right? So -1 or +1 is multiplied by cosine here. So that would be ±1 multiplied by cosine shift, right? And here, this phase is not changed and the signal is left as a syn signal, right? So that would be ±1 multiplied by syn signal. Then we add them up together and we obtain the very same result as in this formula, except for this ratio, right? Which can be multiplied to the signal after adding up together, right? Somewhere here, which is 1 divided by square root of 2, which normalizes the energy, sets it to 1 for each signal, right? Because basically, let me show you what's the catch here and how this number was actually obtained. Because basically, we need that signal to be on the circle line with the radius of 1, right? So here is 1, here is 1, and also each point is therefore on this circle line with radius 1. Now, however, we calculate projections to the x-axis and y-axis, which happen to be, according to the cosine of the angle P divided by 4, exactly 1 divided by square root of 2, right? So this is actually cosine of this angle. Well, that's from the school trigonometry, right? And that's why this factor is this, so that the level of the output signal is 1. Otherwise, if this would be 1, then we would have greater radius, right? So assume that here we have radius of 1, not radius of 1, but projection of 1, right? And this would be also projection of 1, and therefore it's not difficult to calculate that the radius or the energy of the signal would be actually square root of 2. Well, that's according to the Pythagorean theorem, right? And that's why we also need to normalize by this number. After this normalization, the output is with amplitude 1. So Let's see how this works. Consider that we send, for example, this information represented by 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, I mean 1. So this symbol comes to the first channel, and well, it seems that actually odd symbols came to the first channel, and even symbols come to the second channel, right? So this symbol is actually observed at this time moment. However, to the AM1, it comes with a delay caused by this unit, right? So it arrives to the input of this AM1 block one time interval later, right? The next thing, actually let me mark that with green so that it would be more clear, right? So this is green one. And the second symbol happens at the same time moment, but it's not delayed, so it comes to the AM2 at the same time moment. And these two symbols now are arrived at the same time, right? So as I told you, we are using NRZ, meaning that 0 is converted into +1, which is the case here, and 1 is converted to -1, which is, for example, this one, right? -1, -1, -1. And these two pulses are then used with their amplitude to generate accordingly plus sin for this duration. That would be sin signal. Sorry, cosine signal. First channel is cosine, not sin. So that would be cosine. Right? And the second channel generates sin with positive amplitude of the same frequency. Then we add them up together and obtain also harmonical signal. So here you can see example how it will look like. So you can see that this is neither cosine nor sin. It's actually initial phase of p divided by 4. So it starts here, right? Next one is 1, 0, and it had the initial phase. Okay, 0, 0 is this one, and 1, 0. Actually, it had minus p divided by 4 initial phase. So this means that actually it's half of the period later, right? So here we have half of the period, right? And that's when it continues. So you can observe also the phase shift. Okay, yes, so we have phase difference here at this time moment, the change of the phase. That's naturally because the modulation type is phase modulation, right? And that should have these phase changes here and here and here and so on. Now, each of these signals, as I have told, contain information of two binary symbols. And that's how the information is sent twice as fast compared to usual binary phase shift keying. Now we need to receive that signal, and for the receiver part, actually, according to our observation that the QPSK signal can be represented as two binary phase shift keyings, and even more so, what's an important additional observation is that we are using here sin of the some carrier frequency, and here we use cosine or vice versa, because this plus sign actually can be performed in any order, right? So what's important here is that sine and cosine are orthogonal functions, right? Meaning that we can easily separate these two signals one from another. And that's what exactly is done here. So you can see that we send both here and here that signal. However, this receiver is set to work only with cosine, and it will just ignore this second one. And this receiver will ignore the first one, right? So here you can see that we recover the carrier signal, then we change sine into a cosine with this phase shifter. And here we don't change, so we are left with sine. Then we multiply what we have received with ideal signal, with carrier signal, very same way as we did that in our software in MATLAB. Then we perform filtering and integration. So basically that's where we calculate that correlation integral, of which we talked before, right? And then we read the correlation integral value at the end of the symbol. Then we compare it with 0, because we are talking about phase shift keying, so we need to compare with 0 and see the sign of the signal, right? That would be the first bit. Now the same works here. However, please note that here we have an extra delay line, because at the current time they contain both either 1 or 0, and we need to put them in row one after another. And since we already introduced delay for the cosine channel before, here you can see that, now we need to equivalently delay the second channel as well. And that's why we add this delay line here, not here, because this way we would actually delay twice the original signal, which would give incorrect data. Now, however, this was delayed at the transmitter side. This wasn't delayed, and at the transmitter side that wasn't delayed, and it's delayed at the receiver side. So this way these symbols arrive again in the correct order as they have been sent here, right? So that's how we restore that correct order. And well, nothing difficult about this approach. Also, please note that even though we have 4 signals from S1 to S2, we only need to calculate 2 correlation integrals anyway. And that's actually very good, because the same approach would be used for quadrature amplitude shift keying. And for example, we can actually design QAM 1024, meaning that we have 1024 different signals, and we still can do nicely. And what means the most is that optimally, so the best way possible, with just of 2 correlators. So here we would have correlator 1 and correlator 2, either way. Yes, we don't need to make 1024 correlators in our receiver. So this technical simplicity is also very important consequence of the representing signal in this form, right? So we did that intentionally, so we can make our receiver as compact and easy as possible. So the further development of the quadrature shift keying is quadrature amplitude modulation. In this way, we have not only different phase, but also amplitude. For QPSK signal, our amplitude could be either +1 or -1, and nothing else, for both channels. For quadrature modulation, now we can have +-1, +-3, +-5, and so on, different amplitude values. And that's how we create different phases and amplitudes. So let's consider, for example, QAM-16 modulation type, which can be, well, just as well to be considered as the easiest example. Actually, let me tell you that you can consider QPSK to be QAM4 because, well, we have 4 different signals in quadrature approach, and even more so, you can consider binary phase shift keying to be QAM2. Well, basically because 2 is also a power of 2. It's 2 power of 1, right? So QAM-16 is the most, not QAM-16, but QAM-M is the most general case of these modulation types. Now, for the phase shift, we have the same 2 orthogonal carriers, sine and cosine, as before. Now, however, each of these sine or cosines is multiplied not by +1 and -1, but +1 -1 or +3 -3, right? So we are talking about this formula. So here we can now have +1 -1 or +1 -3 in both positions. Different amplitude. So that's why it also is called quadrature amplitude shift keying. That's how this A letter came in the name of the modulation type, because basically it's still quadrature modulation, but now it also changes amplitude. So we have in total 16 symbols, and for each symbol we use 4 bits, and that's why it's 4 times faster compared to binary phase shift keying, which is now a good amount, because consider that our binary phase shift keying could be 100 megabits per second, and then for QAM-16 you would get accordingly 400 megabits per second, which is a lot faster, right? So that is a good bonus. Now the drawback, as you know, is lower noise immunity, but if the distance is not large, then we can afford it. And the constellation diagram now is formed as follows. Please note that once again we are limited by this circle with the radius of 1. And this is necessary to calculate correctly the energy. So if you remember, then bit energy divided by noise spectral density was SNR, and we needed this noise spectral density to calculate correctly sigma in order to generate noise with RAND-N function. Right? So here we need to evaluate the average energy of all these signals, right? So the average energy will be dependent on the total radius, and we assume that this total radius is set to 1. Accordingly, each of these amplitudes needs to be calculated correctly, right? And also, please note that we generate this signal, as I have told you, by setting values from -3 to +3. So basically, we need some multiplier to force this point to have the radius of 1, right? Because otherwise, well, it would have amplitude of 9 plus 9, right? Which is 18, and which is 3 square roots of 2. And we need, therefore, multiplier of 1 divided by 3 square roots of 2 to each of these signals to force it to have amplitude of 1. That's the normalizing factor, right? But also another thing you need to see here is that we are still using gray coding between these neighbors. right? If we watch horizontally or vertically, the neighbor symbol pairs differ only in 1 bit in any possible way, right? So you will not find any pair in this picture which is near to each other, and we look at the direction of the well, either horizontal or vertical. We are not considering diagonal direction because that distance is greater than these short distances, right? So we only take into account the shortest distance symbols. And that's why actually this is the best possible arrangement of the signals, because, well, in this case we can provide actually equivalent distances between each symbol, right? Alternatively, we can try and design different constellations. So let me, for example, show you a so-called circular QAM-16 diagram, right? So you can see here also 16 points, also, well, not really, as you can see, not in gray coding, right? So if we watch on these two symbols, well, they differ in more than 2 bits. However, also, this is not the shortest distance. The shortest distance is here, right? Or maybe even here, and here, and here. And some symbols have longer distances. Well, basically, this is an alternative, right? Which has its own benefits and drawbacks. It's used in some specific standard, right? And it's called circular quadrature amplitude modulation. And well, I just wanted to show you that there is actually a way to make it different way. Also, please note that this is called a rectangular constellation, right? Because, well, actually it resembles rectangle, right? Actually, in this particular case, it's a square. So this is a rectangular QAM. And you only will get this rectangular QAM shape in the case when the number of symbols m is actually the power of 2 or something. So for example, like 4, 16, 44, 64, I mean, 258, because all of these numbers can be represented as squares and powers of 2 at the same time, right? So basically 4 is power 2 power of 2, 8 is 2 power of 3, 16 is 2 power of 4, and so on, right? But what happens for other powers too, such as 32, 128, and so on? In this case, you will not be able to fill completely this square, and you will have some blank points. So, for example, you can see here 32 QAM. As you can see, we are missing some points here, because, well, actually, that would be 36 points, which is not power of 2, right? We have power of 2 equal to 32 with 4 missing points, and that's exactly these points we are missing. But still, it's even more energy efficient because, well, our circle line now goes like this, where circle line represents the energy of your transmitter, right? So, which is limited. And that's why actually this approach would be better. It would be a more efficient usage of energy, but it will not be just as good protected from errors because, well, we don't have as many signal points with large distance, right? So for quadrature, for rectangular approach, the protection is better, but the energy is also not consumed so efficiently, So it's a choice. Either you need more efficient energy consumption, but lower protection. Yes, because, well, here we have absolutely precisely same distances for each of these points, right? Because, well, that's how it is organized. For circular constellation, there is no more such guaranteed minimum distance. Yes, some points have longer distance, some points have shorter distance, but overall the energy consumption is more efficient. And well, of course, as you imagine, generation of this signal is also more problematic, more difficult, right? As well as detection, but well, it's still a way to do it, and some manufacturers really do that, right? So as for modulation and demodulation diagrams, it's basically the same, excluding this one thing that here for IM1 now we generate for QAM-16 case, we generate not NRZ, but a so-called 2B1Q code, which we talked at the beginning of our lecture. So basically, that would represent level of +3, that would be +1, -1, -3, right? And we do that for each part, real part or imaginary part of the complex plane where we draw this constellation, right? So basically, this also can be considered as a real part and this as imaginary part of the complex number, right? And therefore each signal can be represented in analytical form as real part plus yod imaginary part. And we don't even need to carry on those cosines and sines. We can calculate this way this signal and add noise to it directly. Right? That's what we are going to do in our practical exercise today. And for conclusion, let's see what kinds of modulations are used for different applications. For example, cable television, DVB-C standard, which is also used in Europe as well, of course, supports modulation types from QAM-16 to QAM-256. Right? Meaning that we have 256 signal points. You can imagine that they are quite densely packed. You will see in the next picture comparison what that can lead to. And also we have different channel bandwidth. So from 2 to 10 megahertz with a step of 2. That basically defines the quality of video. Obviously, the higher the bandwidth, the higher quality, the higher bit rate of the video to be transmitted, right? And well, you can see here what actually data rate can be achieved for given modulation type and specified bandwidth, right? So if we use 256 quadrature amplitude modulation with 10 megahertz bandwidth, then we can actually achieve 64.11 megabits per second, which hopefully should suffice for HD quality television, right? So for this data rate and binary phase shift keying, you would need much larger bandwidth than this 10 megahertz bandwidth, right? So basically, you can see here that we are, at least theoretically, we should have expected to achieve 80 megabits per second. But due to some filtering, coding, and so on, we are left with practical value of 64.11. How I calculated this 80 megabits per second? Well, very simple way. We have 256 QAM, which gives us 8 bits per symbol by calculating this logarithm, right? and we have 10 megahertz. So we multiply 8 by 10 and we get theoretical capacity of 80 megabits per second. Capacity is the highest possible value which can be achieved in this channel. Of course, usually we don't use full capacity of the channel because of different factors, because such as filtering, noise, of the coding which transmits non-useful information for user, right? Coding is useful to correct errors, but the user itself is not usually interested in these checksums, in these control symbols, and so on. So we are left with only part of this capacity, which is still quite high, right? Now, if we increase the number of points, as you can see from this picture, then it's becoming more and more difficult to distinguish them. So for QPSK case, it was quite easy to see which received signal belongs to which. Because, well, what happens when you send the signal in noisy channel is that from this central point, it can actually, because of the noise, be any of these points. So we have entire region where noisy values belong to, right? And then detector, optimal receiver, works in a very simple way. It calculates, for example, let me mark this point, right? So what does receiver do? So basically it calculates 4 distances. Distance to here, distance to here, here, and here. And then chooses the shortest distance and assumes that, okay, that means that the data transmitted was, for example, 0, 0. I'm assuming that 0, 0 was assigned to this point, but it could have been another thing. Now, if we have QAM-16, we have in the very same energy limits, right, which are here, energy, packed, let's just say so, more data points, more constellation points, right? And therefore, it's somewhat more difficult sometimes to compare these points, right? So it's not a problem here, maybe. Well, okay, let's see what this point, right? So this is very close to uncertainty because, well, we cannot be really certain that it was here or here. And that's where the error can come, right? And well, as you imagine, if we go even further, then we can actually make mistake even more often. And then follows QAM 256, which is actually even more densely compressed. So basically, as you can see here, this is here, right? This is just here. And, well, entire this picture would be densed into this region for QAM 256. And that would be literally impossible to receive data correctly any longer. In this case, we already have many errors, right? So as you imagine, it becomes more and more problematic to receive data correctly. But if it's possible to avoid this noise by using some high quality cables, optical fiber, and so on, you will be rewarded for doing so by higher data transmission speed, which is why we are doing that. And basically in optics, as you can see from this link, you can familiarize yourself with that. We are often using this modulation type as well in high order of modulation because, well, it can provide higher data rates, and we use optical networks as backbone networks for our communication systems nowadays a lot, right? So here is some comparison with efficiency and noise performance, right? So the error 1 per million symbols, meaning that is 1 by 10 degree minus 6 error rate. For 16 QAM would require 10.5 decibel signal to noise ratio. For 64 QAM, that would require 8 decibels more, as you can see. 256 QAM, that would require 24 signal to noise ratio decibel, and so on. So the more points you use, the higher signal to noise ratio you must provide in order to be able to receive with low probability of error. This is good error probability, and if we use, for example, Hamming code, we can correct most of these errors and be okay, and our data will be fine. However, naturally, it's very difficult to provide this signal to noise ratio unless you are sending to some short distances. And how far can we go? How many signals can we use? Already there are standards for home networking, which use up to QAM 4096 signal points, right? Effectively, this means that we send 12 bits per one symbol. And for VDSL2, which can achieve up to 200 megabits per second for copper twistor pair wire, the constellation can consist of up to 32,000 and more signals, different, yes, each carrying 15 bits, right? So basically, that works only over a very short distance, so-called last mile connections, right? And well, this allows us to achieve this high data rate by using usual phone line cable, right? Phone line. It's not fiber optical cable, it's phone line cable. And well, it is working and it's defined in standard. So that would conclude our lecture today. Thank you for attention, and we will continue on practical exercise.